I did the chain sliding off the table problem using Lagrangian mechanics, and I thought it was pretty fun. And I had a great time. And I did point out, hey, there's something wrong about this, and let's see if I can fix it. And I think I fixed it. I would normally do this as a live code, but my program is so messed up, I'm just going to have to show it to you, just so I can move on with my life. Okay, so quick review. Chain on a table. It has 1 degree of freedom. I called that S. And then if you make your Lagrangian, you do have to worry about the changing mass here and the changing mass there, and you have two masses with changing mass. And I did the whole solution. The link to the video is down below, but I got that as my equation of motion, and it was all great, and I had a good time. And I said it was wrong because there's a problem. The problem is that as this part of the chain is moving along, it's not just going to go straight down, it's going to keep moving out a little bit. So the chain's not going to fall straight. It's going to kind of do some floppy thing, unless you have some deflector there, which I said we did. I also said, hey, it's possible that you could model this using something that would represent that. So let me go ahead and show you. I'm going to jump back and forth between the computers here. Let me go ahead and show you the solution that I got before. So this is an animation of the solution. Here we have the chain sliding off the table like that, and that's pretty cool. Now let me show you a real chain on a table. So here's my table, and here's my chain. Yes, it's part of a Mardi Gras bead because I'm in Louisiana. You know that, right? Okay. Chain. So this doesn't work perfectly, but it kind of works. So here's my table. I'm going to hold it right there. And it does show you one problem. But the thing that's nice about this chain is that it's finite masses. And so we can model that in Python pretty easily. So there's my chain. If I let go, let's let the whole thing fall. Right there, you see that it's stuck on the corner because that lip, if I had a flat lip, it went straight down, it wouldn't do that. But I'm going to give it a little pull until it does move. Did you see how that end flipped out? So, I had it on the wrong end too. As that end got over, it went like this, and then this. Since it's moving, that momentum doesn't just stop, it kind of flips out like that. So how can we model this in Python? Well, we can do exactly what you see here with the beads. I can take each individual mass and imagine that it's connected to the next mass by a spring. Now, there's a bunch of issues with this. There's a lot of programming mess with that. So there's a few things I need to do. One, how do you model a string of beads? Not too terribly difficult, and I'll show you the basic idea. The next thing is, how do I get this started? It's not as trivial as you would think. How do I start it like that? And then number 3, how do I model the table? How do I make this not go through the table? Excuse me. Okay, so let's talk about a string of masses connected by springs and how you'd model that. And let's just do this with 3 masses. So imagine that I have my chain consists of 3 masses. Where did I put my chalk? There it is. So I have 3 masses. And I'm just going to arrange them somehow. So the total mass of the string, I can make the mass. The total length of the string, I can make this distance. And then I'll call this distance DL0, or I'll just call it DL. It's the distance between these. And right away you see the problem is that if I have 3 masses, and the length is L, I can't divide by 3 to get DL. I have to divide by 2. I have to divide by n minus 1. So here I have n equals 3. So this length, DL, is going to be the total length, which I called R. You know I called it R because I didn't want to be a Lagrangian, divided by n minus 1. And that will give me the length of DL. And then each of these masses is going to be connected by a spring, so that each of these masses is going to experience a force. And let's say there's no gravity, there's no table, it's nothing. So this would be 1, 2, 3. I'm going to recalculate the force every time. This is going to be force 2 on 1. This is force 1 on 2. Yes, it's the same as that. This is force 3 on 2, and this is force 2 on 3. So for every one of those, I can calculate their force. If I stretch the string, if I pull this way, that's going to stretch this spring, and that's going to make that one move. That's going to stretch this spring, and that's going to make that one move. So the whole string will move that way. Once I set this up for 3 masses, I can do for 10,000 masses. It's not really that much of a difference. Now, my string is special because if you get a long string, it can actually rotate over itself, and it doesn't really care. It can pass through itself. So I'm going to assume it's going to be in a well-behaved orientation. But it doesn't always do that. Let me just go ahead and show you what this looks like because I got it running, and then I'll go over the rest of these pieces. And again, I would love to do this live coding, but it's just too messy. You don't want to see that. If you want to see that, if you're like, hey, go back over, spend 45 minutes and rebuild the program, and everyone wants me to do that, you know I'm going to do whatever you want to do because that's just what I do. Okay, so that's the previous program. I did get this to work. I didn't fully test it. Don't worry about the code. I'll go over the code in just a little bit. Let's just run it. And this is not in live speed. So there's my table, and there's my balls. And you'll notice it does have some weird behaviors right there. But the most important thing is it's sliding off the table. It's not completely well behaved. And then that end flips out. I'm kind of happy with that. Okay, that's kind of good. So how do we model that? Let me go back over to the spring idea. So how do I count? What's the actual equation for calculating this? And you'll notice that if I have a length of 10 masses, the ends are going to be treated differently than all the middles because they only have one spring attached to them. But in general, if I want to calculate this force, and I always get this backwards, but let's say I have 1 and 2. Let's call that the position 1. This is position R1, and this is position R2. So the first thing I need to do is get this vector from here to there. So I'm going to say R1 to 2 is going to be vector 2 minus vector 1. Now for the spring force, F21, I'm going to write that as K, the spring constant, times the magnitude, I'm going to write this as symbolically 1, 2, minus DL, right? So that's a scalar value minus a scalar value. That's how much it's stretched or compressed. And then I need to turn this back into a vector, so I'm going to multiply this by the unit vector R12 hat, the unit vector going from here to there. Now again, I have to think, is this positive or negative? So if this is greater than DL, it got stretched, then this thing would be positive, and so it would pull it in that direction, so that's correct. Now when I go over here to this one, I'm going to recalculate the force 1, 2, even though it's this, and switch the order. So this is going to be 1, 2. So it'll give me the correct orientation in the other direction. And that's how I calculate the force. So that's the first issue right there. How do we build a spring? Now, if I have 20 masses, I'm not going to have mass 1, mass 2, mass 3, mass 4, mass 5. Although you could do that. Okay, I put them in a list. And so that makes some extra problems too, especially with the next situation. Let me show you. And then I'm going to go over all the code, and I'm going to give you the code, okay? So don't worry, and that's where we are. So the next thing is, suppose I have a table, and I have my fake chain like this, and it has a length of R, and this is a distance S. And I want to break this into masses, right? Well, if my mass, let's say I have 5, let's say R is equal to 1, and N is equal to 5. So I'm going to put 1, 2, 3, 4, 5. And I want them evenly spaced. Okay. So the first thing is, what's DL? How do I find DL? Again, I already said that. DL is going to be R over N minus 1. So in this case, DL is going to be 0.2. So this distance is 0.2. So I'm going to have 0.2, 0.2, 0.2, 0.2, and let's say S is 0.2, okay? So, but that's going to be 0.2, 0.4, 0.6, and this should be, oh, I actually could have another one in there. But the point is, it may not exactly fit. It may not exactly fit the length of my chain, okay? I want to definitely start with one mass at the corner, I don't know why I put it that way, but it seemed to make sense to me because I didn't want to have something weird happening. So how do I build this so that I get one right at the corner, even if it doesn't start right here? So what I did was I started with a vector here. I moved over, I moved over, I moved over until I got to the end here. And then I started building my list from here till I got back over there. And that's going to make my spheres in my list in the correct order. And if I just have them in all mixed up, I can't say, oh, the spring force with the next one and the next one and the next one. And then once I got over here, then I went down until I got to the end of there. So that's what I did. And it seemed to work. Okay, I have one more issue that I need to work out. And that's how do I make an interaction with the table? And I do want to point out something, okay? If I say these masses are not allowed to move up and down because they're on the table, I don't have to calculate the gravitational force, they're just not allowed to move down. These are allowed to move down, so they'll pull. Well, even if I have a diagonal situation, like that one's pulling that one, well, it's going to pull back the same amount, and the net force on the whole system in the x direction is 0. So it's not going to move. If you don't have any net force, it's not going to change its motion. It's not going to change its motion. So it's not going to do what I want. There has to be an external force on the system in the direction of x in order to increase the momentum. What force pushes it in the x direction? That's a good question, and I didn't really even think about that until I did this problem. What force makes the chain accelerate that way? What do you think? I'll give you a hint. Let's go back to the half Atwood machine, because it's like a chain, right? So here I have a mass on a frictionless table and a mass hanging down there, and it does something similar, but much easier. But at this point right here, when I release it from rest, this has no momentum in the x direction. And then at the end, it does have an x momentum. So what force made this increase in speed that way? You could say the tension. Well, but the tension is an internal force, although it's not, right? Because the tension on this and the tension on that are in different directions. And the answer is you have to push on the system right here at the point of the pulley. So there is a force pushing on it, and it does have an x component. So what makes this thing accelerate in the x direction is the table. The table pushes on it, and that's kind of cool. But that means that I'm going to model my table as a spring. So here's my table. And I'm going to break it into 3 sections. So I'm going to say this is a negative dl. I don't know why I picked it dl over 2. Negative. This is negative dl over 2. That's negative dl over 2. So if a ball is right here and it goes below that region, there's going to be an upwards pushing spring force. If a ball goes over here and it goes into this region, there's going to be a positive spring force, and that can happen. Since these masses pull back on it, they can swing back in. So you got to be careful about that. That can happen. And that was my original problem. I had these masses, and they would come back over here to negative x, and I would set their position to y equals 0, and they just pop up here. Explosion, bad. Okay. And then in this region, I have a force pushing that way. Okay, so I have an upwards pushing force in this region. At the corner, it pushes at an angle if the mass gets into that region, right? So it's just like a spring. This is a spring table. Tables are springs. Okay, I think it's time to show you the code. Let's go over the code. I'm going to explain myself. I'm going to give a presentation, and hopefully you'll be happy. I'm at least content. I spent way too much time on this. I tried a bunch of different things. And it's, again, remember my programming philosophy is that I want to do things as simple as possible, not as best as possible, because I want people to understand it. And now that's the problem here is it's not completely understandable. Let's just go over the code. Okay, so I'm using WebVPython. I'm going to give you the code. I'll try to add some comments in here. These are just my parameters: the mass of the chain, the length of the chain, the starting location, the number of points. And I did check this for low numbers. I counted them to make sure it was working, and it does work. This is okay, if I have a bunch of masses in a line, I want the spring constant of my chain to be some value, because it does have a spring constant. And then that means that the spring constant in between these is going to have to be some smaller number. Wait, it has to be a larger number, wouldn't it? Well, I did k over n, and I think that works. If I have, well, it's working right now. I don't want to mess with it. I'll think about that again. Gravitational constant, that's just the radius of each point mass. This is the length and height of the table, because I actually drew the table. It's just a box. It's not real. There is no box. There is no table. Corner, I put some spheres over there just to kind of like mark where things were, so that when I'm setting it up, and you can still see them in there, I didn't take them away. RT is my initial position that I move around to put those spheres in different locations. BE is another marker. DL. Balls is my list of balls, right? So the list can be super powerful in WebVPython, because you can add spheres in there, and then you can go through the list and update their momentum and do everything like that, and it's pretty cool. So this right here, this while rt.x is less than negative r minus s, this moves my vector location to the end of the string on the table. And then I can start there going to build my balls. And that's what I do right here. So I add my list of balls and move my vector over back till I get to where I started. This dot on, it was my initial way to say, is it on the table or is it off the table? And it was a Boolean value, and I just took it away. I don't use it actually, but I do give it a mass over here as a property of the sphere. I give an initial momentum as property of the sphere, and then that on-off Boolean value that I don't even use. And then over here, what I'm doing is I'm doing the balls hanging down below. So this stuff from 36 up just sets up the balls. It puts their positions, and it adds them to the list. Pivot is just a point that I don't even use. But I was going to use that for the corner part and make a spring force, so I took that out. I do need a small DT, because if your DT is too large, you're going to let your balls go into the table too far, and things are going to get out of control. So, okay. So other than that, it's not too bad. Right here, line 48, this calculates the spring force on the first ball. Okay, on that first ball right there, and that's the first one on the list. And it only has a spring force to the next ball, which would be ball number 1. So this is ball 0, this is ball 1. So it has that spring force, and then it also has the gravitational force on it. They all have a gravitational force on it. Balls -1, if you have a list of balls, this is ball 0, this is ball 1, 2, 3. The last ball is -1. So I just do the same thing with ball -1, ball -2, the second to last, and other than that, it looks the same. And then this list this loop for I in the range goes from starts with 1 right here, the second one, and goes up to n-1, which is the second to last ball, and it calculates all the forces. So I calculate the vector to the left and right ball, and I use that to calculate the force, and that's all right there. Now this line 55 is another loop that goes through each ball to see if they are inside the table and if I need to push them out. And so I had that exclusionary range, right? Just so that I don't have a ball that's in the negative x direction that's way down below that gets pushed up top too much. So that's what that has, a bunch of conditions to check if the ball's in the right region. So it's not so bad of a program, I guess. And then in line 63, I have I update the momentum of each ball, I update the position of each ball, and then I run it. And that's it. Okay, let's run it again, because it is kind of cool. I feel like I'm going to change this to 250. Let's just see what happens there. I played around with the spring constant a bit, and Yeah, see, I get this weird stuff. I think I need a different spring constant for in the table and in between the springs. And you can see some overlapping there, but this thing does do it. Look, it whips out. That's exactly what I wanted. And come on. It's not bad. It's not bad. So let me go ahead and give you some things to think about, some homework here. So homework question number 1, and I didn't do this, so this is for you. Compare to the analytical solution. So that's that. So look at the bottom of that last ball. Just plot its position and calculate the theoretical position and see how much they compare. Cool to see. 2, energy. Is energy conserved? It should be. You can go through and calculate the kinetic energy of each ball, the gravitational potential energy of each ball, and then plot the total energy as a function of time and see what that looks like. Now, there will be some energy stored in the springs because it oscillates, but I would just ignore that part. Momentum. Momentum is not conserved. Right? We know that. The chain starts off at rest. And yes, a falling object is going to increase in momentum because of the gravitational force. But this should also have a force pushing in the x direction. And then finally, play. See if you can get it to work better. Change the parameters, change the spring constant, change the number of masses and all that stuff, and see what you can get. But there you go. I'm happy enough. Sorry it took so long. I'm going to do some more videos. Just kind of, when I do a video I'm not super happy with, this one's I'm not super satisfied with. I like to make another video to kind of like buffer that one up. But that's just what I'm going to do. So there you go. Hope you enjoy that. So this is part of my classical mechanics lecture course. The playlist is down below if you want to watch all the other videos. And I will put especially the link to the previous chain on the table video so you'll have that. That's that.